This video is part 1 in a series about using simple continued fractions as part of the process of generating Pythagorean triples. We'll write a problem statement and discuss Euclid's formula for generating Pythagorean triples. In the next part, we'll see how to use Euclid's formula in conjunction with simple continued fractions to generate triples. Let's get started. As background, if we have a right triangle with the lengths of sides A, B, and C, the lengths of the sides obey the theorem of Pythagoras. This theorem tells us that a squared plus b squared equals c squared. Our problem statement is straightforward. We want to find three integers, a, b, and c, that satisfy this equation. Here are some examples: 3, 4, and 5, 5, 12, and 13, and 8, 15, and 17. You can generate more from these by multiplying each term in the triple by the same number as long as you end up with three integers again. For example, if we multiply each term in this triple by 2, we get 6, 8, 10, another triple. And if we multiply each term in this one by 2, we get 10, 24, 26, also a Pythagorean triple. And if we multiply this one by, say, 3, we get 24, 45, 51, another triple. When the three numbers in the triple are coprime, which means they don't have any common factors besides 1, the triple is primitive. These three are primitive. None of these are, though, because they share common factors. We could divide these two by 2, and recover these, and divide this one by 3, and recover this one. We are seeking integer solutions, whether the triple is primitive or not, so this is a Diophantine equation. Now let's talk about Euclid's formula, which provides a way to generate Pythagorean triples. All you have to do is pick two integers, which will denote m and n, that satisfy this condition. M is greater than n is greater than 0. Then you can generate Pythagorean triples using these equations. A equals m squared minus n squared, b equals 2 times m times n, and c equals m squared plus n squared. That's it. Let's use this table to look at some examples. We'll have rows for m and n, and for a, b, and c. In the rows for m and n, we'll put every combination where they are less than 5. That should be enough to illustrate this. Let's do the first one when m equals 2 and n equals 1. A equals m squared minus n squared equals 2 squared minus 1 squared equals 4 minus 1 equals 3. B equals 2 times m times n equals 2 times 1, which equals 4. And c equals m squared plus n squared, which equals 4 plus 1 equals 5. It generated this primitive triple. Here are the other results. I'll leave it to you to check most of the calculations if you like, but let's show the work for the last one. A equals m squared minus n squared equals 4 squared minus 3 squared equals 7. B equals 2 times m times n equals 2 times 4 times 3 equals 24. And c equals m squared plus n squared equals 4 squared plus 3 squared equals 25. Some of these triples are primitive and some are not. These are primitive. They do not have common factors greater than 1. These are not primitive. The terms in this one, for example, have 2 as a common factor. If you divide through by 2, you get 4, 3, 5, a primitive triple. When you use Euclid's formula, the resulting triple will be primitive if and only if these conditions are met. M and n are coprime, and exactly one of m and n is odd. Let's look at our results that are not primitive. In this one, when m and n were 3 and 1, they did not yield a primitive triple because the two of them are odd. They are coprime, but they don't satisfy this condition. It isn't true that exactly one of them is odd. In this one, 4 and 2, the other pair that didn't yield a primitive triple, doesn't satisfy either condition. They are not coprime, and it isn't true that exactly one of them is odd. In the next video, we'll see how to use Euclid's formula along with simple continued fractions to generate triples. In this video, we wrote our problem statement and discussed Euclid's formula for generating Pythagorean triples. That's all for now.